Welcome to the world of chemistry and the empirical world, which means that we do a lot of measurements. Numbers are the words or the language of measurement. So we need to understand numbers in order to communicate in chemistry. We need to understand the basic operations that we would use the calculator for. So we have recommended a TI-30XA calculator. These are available about $10 or $11 at the store, and they're called a scientific calculator. So since chemicals is an empirical science, we must know that numbers can be big and they can be small. The number system uses place notation in order to communicate the size of something. We are familiar with the $100 bill. We know it's 1 followed by 2 zeros, or the $10 bill, 1 followed by 1 zero, or the $1 bill. They all have the digit 1 placed in a specific place to understand the value of that amount of money. So let's compare the English names and the metric names for the place of numbers. Now we have the English system, and we have this large number here. And here is the decimal point, and this is the ones place, the units place. You may know over here, here's the thousands place. This has a hundreds place, and all the way over here to the billions place. So it's very significant where the number is located to understand the meaning or the size of the number. Those on the right of the decimal point are smaller than a unit. They're fractions. So this is the tenths place, 1/10 divided by 10, and this is the millionths place. So how does this correspond in the metric system? Well, in the metric system we have exactly the same place notation, but it has a different name. And so you note that the billions place is the giga place, and notice that that's a capital G. That helps you remember that a capital G means it's big. Or a mega. Mega corresponds with millions, capital M. Or a kilo corresponds with the thousands place, and capital K. And then we go down to smaller units, and we have down below here we have the deci, which is 1/10 of a unit, or the centi, which is 1/100th, or the milli, which is 1/1000th. And all the way down to the nano place, which is 1/1,000,000,000th of a thing. So the place notation is very, very important to understand the size of numbers. And since in chemistry we deal with big numbers and small numbers, we're going to have to get an order of magnitude to the numbers that we use. Let's look at the same expression here, showing the powers of 10, because our number system is based on powers of 10 in the base. And if you look down here, what was the billions is 10 to the 9th. What was thousands, kilo, is 10 to the 3. What was millions, or milli, in the metric system is 10 to the -3, small. So the place notation could be thought of in terms of a certain power of 10. And this particular aspect, this image, I think is something we all need to do when we're dealing with numbers and scientific notation. Our next consideration is, can we convert numbers that are in decimal notation to scientific notation? And let's make a definition of scientific notation. Scientific notation is a number which has between 1 and 10, a number between 1 and 10 in front, multiplied by some power of 10 that would indicate what place that it's in. Let's take an example of a number, and let's use the number 2,000. We know that if you look at 2,000, it's written in this way, followed by 3 zeros. That's the decimal notation. Well, in fact, how are we going to indicate it in the scientific notation? We just write the number 2 and then times 10 to the 3, because 10 to the 3 indicates thousands. Sometimes people wonder why you might want to, how would you know to use a 3 for the exponent? And an easy way is to look at the decimal and move it over. 1, 2, 3. You have moved it over to the left 3 places, and so that indicates a positive 3. How do you get scientific notation with a negative exponent? Well, let's look at another number. This other number is 0.0045. That's the decimal notation. It is a small number, so we're going to expect it to have a scientific notation with a negative exponent. And in fact, it is 4.5 times 10 to the minus 3. In fact, we moved the decimal point 1, 2, 3 places to the right to get 4.5. And so in fact, converting from decimal notation to scientific notation is just a matter of knowing what place and what exponent. And a little practice will make it easy for you. One of the other aspects that we might ask ourselves would be, could our calculator do this? And so we'll go back to looking at the calculator. Be very nice if the calculator could do this for us. So I'm going to start here. I'll get this set up here. Let's just go back to the same number that we have, 2,000. And I'm going to enter 2,000 into here. 2, 0, 0, 0. And so you see in the display 2,000. That's decimal notation. Now I'm wondering, could I make it say 2 times 10 to the 3 scientific notation? Well, yes, I can. On this particular calculator, you'll notice these keys above here indicate the kind of notation. And so all I would need to do is hit a second function and then a 5, which it gives it scientific notation. And if you can see now, the number has been changed. The number now is 2, and then a little superscript is 03. Get it back. I'll go to floating notation, which is second 4. I'm back to 2,000. And so our calculator can actually convert something from decimal to scientific. That'd be second 5, or from scientific to decimal, that would be second 4. Let's try one more just to make sure. I think the other number I had was 0.0045. 0.0045. There's that number. And let's enter that into scientific. Second 5, and that is 4.5 times 10 to the minus 3. So now, as we consider our options here, we see that we can express numbers as decimal or as scientific. And when would it be necessary to express a number in scientific notation? Well, one example is that take a number that you cannot actually enter in decimal notation. Let's take the number 500 billion. 500 billion. That would be 500 with 9 zeros behind it. I can try that. I can put 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The first two were 500 and then 9. And notice I can't enter any more. I keep entering 0 and nothing happens. My calculator only has the capacity for 10 digits, 10 places. And so to enter that number correctly in my calculator, I'm going to have to enter it as scientific notation. So let's take a look and see how that would look. 500 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the way it will look in decimal notation. Pretty big number. And I know that it would look like this in scientific notation. 5's 10. And let's see, it'll have a big positive exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, times 10 to the 11. So if I want that particular number in my calculator, I'm going to have to do it in a certain way. And I'm going to have to use a key called the EE key, enter the exponent. So I would say 5, enter the exponent, 11. So 11. And you can see then it says 5 with the superscript 11. So that's 500 billion entered into the calculator. I can try to change it to floating notation, but it won't happen. It won't work. Too large of a number. Now, the only other thing we have to know about entering a number would be to pick a number that requires a negative exponent. And let me give you another number. We already know this number, and we know that would be 4.5 times 10 to the 1, 2, 3, 10 to the negative 3. So if I entered that number directly, I would go 4.5, enter the exponent, and then you have to use this particular key. It's not the negative operation key, it is the change of sign key. Change of sign 3. So there that is entered in scientific notation. This number I can change to floating to decimal notation. Second 4, you see it gives me 0.0045. So our calculator can enable us to enter numbers that are bigger than 10 places or smaller than 10 places. So we want to use our calculator correctly, and I've shown you the keys to do that. Practice will make perfect. When you write down a number from a measurement, the digits you record should be only those required in order to convey the meaning of that number. So only digits that are significant should be recorded. Now you'll find one thing about a calculator, it always gives you 10 digits, and most of them will be insignificant. So the concept of significant figures is going to be important in measurement. So how do you count the number of significant figures in a number? Well, it's very important to be able to do this. For the first thing that you have to understand is that all non-zero numbers are significant. So if it's not a zero and it's recorded, it's significant. And some zeros are significant. So in order to know which zeros are significant, we're going to have to classify the zeros. There are 3 kinds of zeros. There are preceding zeros, those in front, way to the left, before any number other than 0 appears. And they're sandwich zeros, zeros that are in between 2 numbers, and trailing zeros, zeros that are at the end of a number and have no number following it. So the important idea is that all preceding zeros are not significant. They're just placeholders, so they're not counted as significant figures. Sandwich zeros are always significant. And trailing zeros are significant only if the number has a decimal point. So let's take an example and see if we can use these classifications. We're looking at this number, 0.005030. I put a lot of zeros in there so we can make good decisions. So the very first thing is that we clearly have 2 numbers, so we have 2 significant figures, the numbers themselves. But now let's look at the zeros and classify them. In the front here, we have preceding zeros, 1, 2, 3 of them. They're just placeholders. They don't count. In the middle here, we have a sandwich zero, sandwich between 2 other numbers. That definitely counts. And we have a trailing zero and a decimal point. So that also counts. So therefore, if we were to say the number of significant figures in here, we don't count these, 1, 2, 3, 4. This number has 4 significant figures. That was fairly easy. I have also a couple other little examples. One is the number 700. This is the number 700. How many significant figures does 700 have? Well, obviously 7 is significant, but we have 2 zeros, and they are trailing zeros. But the trailing zero without a decimal point. You don't see a decimal point. And so this particular number has only one significant figure, the 7. The zeros are trailing without a decimal point. It's very, very important that we understand how to get the number of significant figures. The importance comes from calculation. Let me show you an example of calculation. The rule is that when you multiply two things together, each is a factor. The answer should have the same number of significant figures as the factor with the smallest number. I'll probably repeat that, but how many significant figures should your answer have? And this is the key idea. So when you multiply or divide, the answer should have the same number of significant figures as the factor with the least. So I'm going to take an example. Here's 2.07 times 27. And I look carefully at this factor. It has 3 significant figures. The 2 and the 7 and the sandwich 0. This has 2 significant figures. When I multiply them together on my calculator, and I put this like the calculator window, this is what I get, this huge number. Well, you should not record that as the answer because most of this is insignificant. In fact, the rule says that my answer should have 2 significant figures because this factor has only 2. And so I have to really write my answer down to be 56. And then you say, oh, but it was 55. When you once decide you're going to have 2 significant figures, you have to stop there and you have to look to the figure at the right. And if it's 5 or greater, then you have to increase this. If it's less than 5, just leave it 5. So since 8 is greater than 5, I had to report the answer to this problem as 56. Here's one more example, and we'll just take a look at that quickly. This example is a division, and again, what we're going to do is that we're going to take 0.0923 divided, that's a symbol for division, by 21. Your calculator has a different sign for division, but it's a division problem. And you can see that basically this number has only preceding zeros, 1, 2, 3, 3 significant figures, and the divisor 21 has 2 significant figures. So if you press this, enter this into your calculator, this is the answer that you get. 0.00, a huge answer. And I make it a practice kind of sometimes to write down on a piece of paper in these brackets what I get from the answer and then go ahead and make the decision what the real answer should be. So the fact that this factor only has 2 significant figures means that my answer should have only 2 significant figures. So I'll look here, and the preceding zeros are just placeholders. So the 2 significant figures are going to be here. And so I look at the 3, and I look one to the right, and I see it's a 9. And so I end up that the answer to this problem that should be recorded is 0.0044. Okay? So we need to use our rules for significant figures because the calculator gives you far more significant figures than you need, and your answer would be incorrect if you recorded all of those numbers.